Welcome back to the Deep Dive. Today we're tackling something pretty fundamental in AI. We're looking at this assumption that deep learning has to be energy hungry and kind of random.
Yeah, that's the standard picture, isn't it? These incredibly powerful models, sure, but they just chew through energy. And they rely on things like stochastic gradient descent, lots of tiny random-ish steps.
Which makes them, expensive to train, obviously, but also inherently non-reproducible. Run it twice, get different results.
And that's a huge problem, especially in fields where you absolutely need reliability, like medicine or critical systems.
Right. If the model changes slightly every time you train it, how can you trust it? How do you get it improved?
Exactly. That variability is a nightmare for auditing and regulation.
Okay, but the sources we're diving into today, they propose something radically different. It honestly sounds a bit like science fiction. A new framework. It's deterministic, it's matrix-free, and they claim it builds the optimal representation in just one go.
One single pass through the data. No iterations, no training epochs like we're used to. It's a complete shift.
So getting rid of gradient descent entirely.
That's the claim. It's a conceptual leap, really. Moving from, let's say, iterative searching to something more like direct geometric projection. So our mission today really is to unpack how this works. We'll need to talk about things like the Koopman operator, this log prime basis,
Okay.
and see how it gets classification accuracy that's, well, pretty decent, 85 to 88% on fashion MNIST, which is competitive with standard CNNs, but with potentially, they claim, 1 to 3 orders of magnitude less energy.
Wow. Okay, let's start right there, that efficiency claim. 1 to 3 orders of magnitude, that's enormous. If traditional deep learning is this slow, iterative crawl, how does this new method actually run?
Well, the advantage comes from avoiding all those steps. They replace the, thousands, maybe millions of tiny iterative calculations with a process that's fully parallelizable. The heavy lifting is done by things like fast Fourier transforms, FFTs.
FFTs. So that gives it a really efficient complexity scaling.
Exactly. It comes out as ON, log n, which is, computationally speaking, very, very good for this kind of past.
And the actual numbers, you mentioned the comparison.
Right. The sources pit this against a standard baseline, a PyTorch implementation of a LeNet 5 CNN on a CPU running fashion MNEST.
Okay, a common benchmark.
Yeah. And that CNN takes about 8.2 milliseconds per sample just for inference. Just make a prediction.
8.2 milliseconds. And this new framework,
It clocks in around 0.05 milliseconds per sample, again on a CPU.
0.05,
It's not just a bit faster. It's a completely different scale of speed.
which directly means huge energy savings, huge hardware savings, especially if you're doing this at scale,
Precisely. And importantly, this speed boost comes with solving the reproducibility issue.
because it's deterministic.
Fully deterministic. For you, the listener, maybe working in, say, medical diagnostics or infrastructure where you need audit trails. It means identical input gives identical output every single time. No random seeds, no stochastic paths causing variation.
Okay, so how? How do they bypass all that iterative approximation to get a single analytical answer?
Well, they found a way to get a closed-form solution. It's done in one step using what they call a tangent space projection.
Right, you mentioned an equation earlier. Looked a bit scary.
Yes. It was $2, 100 plus tau lambda, and S is 1C. But conceptually, think of it like this. $2 is your starting point, your data.
Okay.
Lambda sort of encodes the inherent structure, the geometry, the complexity. And $C is the final optimal representation you project onto.
So instead of searching around randomly,
You calculate the target directly. One single analytical projection replaces potentially millions of tiny searching steps.
that does sound almost too good to be true. Is there a massive computational cost just setting up that projection? Where's the catch?
That's the clever part. The calculation itself is made tractable by 3 core mathematical ideas, 3 pillars that work together.
Okay, the pillars. Let's break those down. What's the first one?
Pillar 1 is Koopman operator theory. It's actually not new. It dates back to the 1930s, but its application here is ingenious.
Koopman. Sounds key. What does it actually do to the learning problem?
It linearizes it. Think about deep learning dynamics. They're incredibly complex, non-linear, like a big tangled mess.
Okay.
The Koopman operator approach lifts the system, mathematically speaking, into an infinite dimensional space. And the real magic, the Koopman magic, happens there. In the right mathematical basis, this complex operator becomes essentially diagonal, a diagonal surrogate.
Diagonal. Okay, for our listeners, what does that mean practically? Why is diagonal good?
Diagonal means decoupled. Imagine your messy system where everything affects everything else. Optimizing one thing messes up others. Diagonalization separates the system's modes, its fundamental components, so they become independent.
Ah, so you can optimize each part separately.
Exactly. That incredibly complex high-dimensional optimization problem. It breaks down into solving lots of simple one-dimensional problems, all in parallel. And they show that optimizing each mode on its own like this actually finds the globally optimal representation for the whole system. It's a huge simplification.
Okay, so Koopman provides the how to compute it efficiently by decoupling. Pillar 2 must be about the what. What does the final answer look like? You mentioned geometric invariance.
Right, and this is all about interpretability. You know how in deep networks the features learned are often these abstract, opaque clouds of numbers?
Yeah, the black box problem.
Precisely. This framework is different. It builds representations from explicit, understandable geometric primitives.
Like what kind of things?
Things you can actually measure and visualize.
Right.
The total mass or energy, the centroid, like the center of gravity, second moments, information about spread, even things like zero crossings.
That sounds much more transparent. You could actually see why the model made a certain decision based on these geometric features.
Exactly. The visualizations in the sources show this quite clearly. A class like, say, E-shirt in Fashion MNIST is represented as a specific combination of a few shared geometric primitives.
And how does it choose which primitives are important?
It uses a variational principle. They call it the Goldilocks score. It tries to find the representation that's just right, meaning it explicitly balances fitting the data well, capturing the data's energy, against minimizing the harm or complexity introduced by distorting these fundamental geometric primitives.
Okay, balancing data fit and geometric integrity, which leads us, I guess, to pillar 3, the log prime basis and this Goldilocks weighting. Why primes?
This is really quite novel. They use a basis inspired by prime factorization. Basis vectors are related to the logarithms of prime numbers, and the key property here is that these values, the logs of primes, are rationally independent.
Rationally independent. What does that buy you computationally?
It buys you exact orthogonality right out of the box, natively.
So, perfect separation. Like perfectly distinct channels that don't interfere, mathematically guaranteed.
That's a great analogy. It means you don't need to do extra computational work like a Gram-Schmidt process to force your basis vectors to be orthogonal. The primes give it to you for free.
Very efficient.
Extremely. And this is formalized by the Goldilocks measure, this Bolijem weighting. It defines the mathematical space, the Waiter-Hilbert space, in a way that captures the data's geometry and allows for, well, exact energy accounting. Parseval's theorem holds perfectly.
Okay, so we've got this framework. One step, deterministic, interpretable, super fast, thanks to Koopman and primes. But let's push back a bit. 88% on Fashion MNIST is good, but Linnet 5 is old news, right? How does this actually perform on harder problems? And what if you really need that last 1–2% of accuracy? Is there a trade-off?
That's a fair question, and yes, the focus so far has been proving the concept that iteration isn't strictly necessary for good performance. But the trade-off is actually handled very elegantly. The framework includes something they call accuracy dialing.
Accuracy dialing.
Yeah. Because the solution is analytical, found in one step, you can control the trade-off between, say, compression and quality using a single parameter, that tout from the equation earlier.
Ah, the harm energy trade-off coefficient.
Exactly. You adjust tout, and you instantly get the optimal model for that specific trade-off point.
Wait, instantly. You don't have to retrain a whole new model if you want it slightly faster or slightly more accurate.
Nope. That's the beauty. In standard deep learning, wanting a different speed-accuracy balance usually means designing and training a whole new architecture, which takes time and resources.
Right, days or weeks potentially.
Here, you just tweak tout on the same underlying model structure, and the optimal configuration for that tout is calculated directly.
So you get this smooth, predictable curve showing the relationship between, say, compression and accuracy.
Precisely. A smooth, monotonic curve generated from a single model structure just by varying that quality parameter.
Okay, now this sounds really practical. And you mentioned something called the compression cliff.
Yes. This is a key finding. Along that trade-off curve, there's a specific point, an equilibrium, that's particularly interesting. They identify it, for instance, around tau Gerald and 1,1 in their experiments. At this point, you might accept a very small dip in quality, maybe keeping, say, 85.5% of the peak performance. But in return, you get a massive disproportionate gain in compression and efficiency. It's like falling off a cliff in terms of complexity reduction.
So it's the point of diminishing returns for accuracy, but maximum bang for your buck in efficiency.
Exactly. It's where the marginal cost of adding more complexity to get slightly more information starts to skyrocket. It finds that optimal economic sweet spot.
That has huge implications for deployment, especially on devices with limited resources.
Oh, absolutely. Think edge computing, IoT devices.
Smart cameras, sensors.
Right. Devices where energy consumption is critical and you don't have massive GPUs. This approach, with its low energy needs and small footprint, remember, no huge weight matrices to store.
Right, the model is sort of implicitly defined by the chosen modes.
Exactly. It makes it incredibly well suited for those resource-constrained environments needing real-time processing.
And we already touched on the benefits for medical imaging, the auditability.
Yes, the determinism and the interpretability through geometric invariance are crucial there.
What about the process of designing the model itself? Does this simplify things? Deep learning architecture design can be a real dark art.
That's another interesting angle. It largely sidesteps the traditional architecture selection problem. How many layers, how wide, connections, etc. Here, the architecture kind of emerges from the data itself during that single projection step. The mode selection process, guided by that Goldilocks score, effectively is the architecture determination. It keeps the modes, the geometric primitives that are most important for the task according to the data's own structure, and discards the rest. It's automatic.
So the data itself dictates the optimal shape of the model in this framework.
In a sense, yes.
And just to confirm, this isn't just theoretical elegance. Does it actually beat standard engineering methods in practice, like for compression?
The sources show empirical results, yes. They compared its reconstruction quality against standards like JPEG and JPEG 2000. At similar compression ratios, this geometric analytic approach achieved significantly higher PSNR peak signal-to-noise ratio, which basically means better image quality after compression. It seems to be a fundamentally more principled way to capture and represent the essential information.
Okay, let's try to wrap this up for the listener. What we've explored today is, well, it feels like a potential paradigm shift, moving away from the familiar, iterative, energy-hungry, often random deep learning process
Towards something that is deterministic, completely reproducible, much more energy efficient, interpretable through geometry, and finds a globally optimal solution in a single computational step.
It's quite a list of advantages.
It is, and the mathematical connections seem profound. That link they mentioned between the log prime basis spectral density and the Riemann zeta function's Euler product. It hints that maybe learning at its core isn't just search, but something more like a deterministic projection onto invariant manifolds defined by the data's natural measure.
So finding inherent mathematical structures rather than just engineering complex approximations.
That seems to be the implication. It points towards what the authors call deterministic intelligence architectures, a different way of thinking about building intelligent systems.
Which leaves us with a really provocative thought for you, our listener. If intelligence, or at least powerful representation learning, can be computed this way as a fixed, verifiable, stationary invariant of measure, not something we have to iteratively search for, but something we can directly calculate. What does that really mean for the future, especially for AI systems where trust, transparency, and frankly, energy sustainability are becoming non-negotiable?
What kind of AI could we build if this deterministic efficient approach becomes more widespread?
That's the challenge, and the question we'll leave you with for your own deep dive.